look at how much bigger an Atlantis page is than a regular page. Because remember that in Atlantis, we're actually asking the page itself to implement more code, right? So a natural question is, how much bigger do pages become, right? And so it is true that Atlantis does make the page bigger. However, the first thing to keep in mind is that caching through the browser cache basically saves 81% of bytes and 75% of requests on average, okay? So what that means is that typically most or all of that high-level runtime is going to hit in the cache. So even if I showed you a number that showed that the runtime is like 1 gig large, after that 1 gig is downloaded, you're good to go. Now, of course, I've set this up such that you're expecting a number much smaller for the web stack, right? That was intentional. I practiced that in the mirror. So how big is the actual runtime stack in practice? So here's the size for that legacy web stack, which I showed you from a couple slides ago, right? In other words, if a page wants to run in this sort of backwards compatible mode, this is what it would have to include, right? And so this graph up here shows the size of the compressed ASTs that are actually sent over the wire. So for example, the HTML parser was about 280K, and the JavaScript runtime was about 200K. And so note that the average web page today is about 1.6 megs in size. So if the browser has a totally cold cache, Atlantis makes the page roughly 47% better. However, as I mentioned, this is sort of a worst case number because typically the cache is warm.
How did you make the parsers at the runtime?
How did I make them?
Yeah.
Oh, so
like take chromes and translate to them to an AST, or did you write them?
That's one thing that you could do. No, I did it from first principles by looking at the spec. But there are tools which allow you to, for example, take C++ code, like Inscription you may have heard of, or things like this, and then compile it down to JavaScript. So that's one option we decided not to take because, as it turns out, that tool chain is fairly fragile, and we wanted to avoid some of that. Over there? Yeah.
It takes about 4 hours to compile.
Yeah.
And it's a bit bigger.
Yeah.
What happens if you actually want to use WebKit?
Well, so you're saying, what if I actually want to use the full-blown sort of WebKit with all its gnarly features? I mean, you could do that. I mean, there's nothing that prevents you from doing that. I mean, one reason why we get a bit of a nice size reduction here is because we have that siphon interpreter, right, which can actually sort of help with some things like image rendering, for example, because it can provide like some higher level interfaces to the bitmap engine. But you could definitely do something like that. And in fact, people do things like that today with things like Asm.js, if you've heard of that. So people try to do things like compile the Quake engine down the JavaScript. And then don't laugh, this is the world we live in, okay? It's filled with sickos, right? And they try to run it in the browser. So long story short, yes, you can do that. I think it would be less efficient in terms of speed, but it's possible.
In the browser right now, like the JavaScript engine and their rendering and stuff, it would be a lot slower. Right? You use a lot more CPU without, like you're sending an unoptimized code, and it could be different for every website.
Yeah. So one thing that's nice about the interpreter is that it can do things like JITting, for example, right? But you're right that if all you did was just send over raw ASTs that didn't have things like JIT in it, then straight line code execution would be much slower. As it turns out, though, straight-line code execution is typically not the most important thing in a browser. Right? We do have a JIT, but it's typically a lot of times these JIT numbers are for what they call benchmarking, right? So that people like Gizmodo get excited about stuff. If you look at what a browser actually does, it's typically not raw execution speed that's important. It's how quickly it can execute a series of event handlers. Right? So imagine like a game that was firing a bunch of animation callbacks or that was handling a bunch of GUI inputs. That's typically the key thing to look at in terms of performance. But you're exactly right that we do need JITs to keep things efficient.
So you mentioned like backwards compatibility. So in the future, if everyone is using Atlantis and someone loads a page that doesn't have this environment tag, it'll still work. So in that transition period, before everybody moves to Atlantis, if I open one of these pages using Chrome, what happens?
If you open...
Like a page that has this environment tag.
Oh, you're saying like if you have an Atlantis-aware page, so that will... Well, let me tell you what could happen, which involves code that I did not write, but what you can imagine happening, right? So what you can imagine happening is that the page itself with the tech that, it's running on a browser that does not support extensibility, and then it could dynamically load this legacy web stack that we have and essentially create its own virtualized environment, if you will, that runs atop something like IE. Now, I did not write that code, but that's the story that you would actually have if you wanted to support things like that during that transition period. Cool. Next, I want to describe how Atlantis makes it easier to provide deny by default same origin policy enforcement. And I want to situate this discussion in the context of the screen sharing attack that I mentioned earlier. So in Atlantis, an origin has to explicitly give permission for external entities to access local resources. So suppose that the browser's running 3 different principal instances, and suppose that the instance on the left is subverted by a malevolent force, okay? Maybe you click on that link to win an iPad, you want a virus instead. We've all been there. I'm not going to judge you, okay? Things do get better. So that principal instance over there is subverted. Now, that subverted instance can goof around with its own bitmap, and it can register its GUI handlers for its own bitmap, and so on and so forth. However, it cannot directly tamper with resources that belong to other principal instances because they're all strongly isolated. So the worst that this thing can do is try to send malicious RPC messages to those other principal instances. However, if you assume that other principal instances are reasonable and don't just sort of do arbitrary things when sort of unexpected RPC messages show up, then nothing should be able to happen to those other 2 principal instances, right? So by default, things like the screen sharing attack should not work, assuming that other principal instances do sort of the minimally reasonable thing. So now I want to discuss one of the greatest features of Atlantis, namely the extensibility, right? Now by extensible, I mean that a web page, memorize that face, I'm telling you. By extensibility, I mean that web pages can change the behavior of the high-level runtime, either to fix bugs, add new features, or in this case, to add new runtime checks that make a page more secure. So once again, here's the architecture for a regular browser. Now what you'll see is that the renderer and the JavaScript engine have 2 separate object heaps, okay? The JavaScript engine has a heap for JavaScript objects, and the renderer has a heap for the C++ objects that it manages, okay? So objects in different heaps can't directly inspect each other's state. So if the JavaScript object at the bottom wants to talk to the C++ object on the left, the JavaScript object has to send an RPC to the C++ heap. Okay, so for example, those DOM nodes that I mentioned to you at the beginning of the talk, right? There's a JavaScript version of a DOM node, then there's a backing version for it in the C++ object. So when the JavaScript world manipulates DOM node properties, it's actually generating these RPCs. And so an example of such an RPC is the inner HTML interface, right? So when JavaScript code assigns something to the inner HTML interface, the renderer will dynamically inject